Here's a fun effect that happens with sound when you have moving objects, and in this video we're going to talk about it. It is called the Doppler effect. The Doppler effect is a change in wave frequencies that occurs when a source of sound is moving with respect to an observer. Now, that's an important point, saying with respect to, because if the fire truck is actually moving, or if the person is moving towards the fire truck, it doesn't matter. You're going to have the same effect. So this video, we're going to look at the effect where the source of a sound is moving. So in this case, the fire truck in this image. So when you have a source that's moving toward an observer, it's going to have a higher frequency and a shorter wavelength. According to, the observer is going to see a higher frequency and a shorter wavelength. The opposite is true. If the source is moving away from the observer, then the observer is going to see a lower frequency and a longer wavelength. Now, let me show this to you using this module. The website's at the bottom. If we go there, here's what it looks like. We have a source here on the left and an observer somewhere in the middle. And we set a velocity to both the source and the observer. We're just dealing with the source right now, so the observer's at 0. So actually, let me put the source at 0 as well, just so you can see what the sound wave looks like. Just a regular sound wave, nothing unusual. In this case, the source is emitting a sound wave with a wavelength of lambda. The observer receives that same wavelength of lambda. You can see here the source wavelength is 1 meter. The perceived wavelength by the observer is 1 meter. Now, let's give this guy a little bit of velocity here. We'll say 150 meters per second. Nice even number. So now what's happening is, as the source moves, by the time the next wave is emitted, the source has moved a little bit further to the right. As a result, the next wave is offset a little bit, and the waves become a little more packed on the right side and more spread out on the left side. As a result, the observer, seeing the source moving towards it, is going to observe a shorter wavelength. Let me go back and do that one more time. The observer is going to be viewing a shorter wavelength and thus a lower frequency, or a higher frequency. And sure enough, you see the original frequency was this. The perceived frequency is much higher. But once the source passes, give it a second, now the observer sees the source moving away. Now, all of a sudden, the wavelengths that the observer sees are much longer, so the frequency is much lower. So a higher wavelength and a lower frequency. So what about the math? Let's talk about the math. If we have an object here that's emitting a sound at point 1, let's ignore it moving right now. Let's just assume it's holding still. It's going to emit a sound wave. Then by the time it emits the second wave, the first wave will have moved some distance d, and that d can be found using this speed of sound, the speed of the wave, times the period of the wave, how fast that wave is moving, or the amount of time between pulses. Okay. Now, let's get it moving. So now we have our object at point 1. It's moving forward with some velocity, emits a pulse. By the time it emits the second pulse, it has now moved over here. So the second pulse is here, and now you have a different wavelength. Oh, by the way, I should say this initial d over here, this is going to equal the wavelength of the original wave. Okay, coming back at point 2, the second pulse is emitted, but now that distance has changed, so we have a new wavelength. So we're going to call that lambda prime. Well, how do we find the lambda prime? Well, by noting that this distance plus this distance equals this distance. So d is the total distance from 1 to the edge of the first pulse. And that's going to equal d of the source plus lambda prime. And so lambda prime then is going to equal d, the distance from 1 to the first pulse, minus d source, the distance that your object has moved. So your textbook goes through the calculations in more detail here, but just note here, d is the distance that of the original wavelength, so substitute with just the wavelength. D of source we determined was just velocity times time. But the time, remember that speed is equal to wavelength times frequency. Well, that also means velocity is equal to wavelength divided by time. Right? Distance divided by time, that's the definition of velocity. So that makes sense. Which means that the period t is going to be the wavelength divided by the velocity. And this would be of the original wave. So you have your period t is going to be the wavelength of the original sound divided by the speed of sound. And you end up with this, that the new wavelength is going to be the original wavelength times this factor of 1 minus the speed of the source divided by the speed of sound. Okay, so we take that and we acknowledge the fact that wave equation, velocity equals speed, velocity equals wavelength times frequency, and likewise velocity equals wavelength times frequency for the new wavelength. And use that, and you get this equation, that an observed frequency, f prime, is going to be equal to the original frequency divided by that that quantity, 1 minus v source divided by v sound. Now note that this was the case when the source is moving toward a stationary observer. What if it were the other way around? What if the source were moving away from the stationary observer? Well, you could do a very similar analysis, and what you'd find is that you get the exact same equation. The only difference is the minus is now replaced with a plus. Okay, so we've got two different equations based just on the direction the source is moving. Well, we can easily fix that problem, and we can combine the two problems. This one is when the source is moving toward the observer and away from the observer. But if we define our velocity to be positive when the source is moving away, then we can just combine it into this one equation, and this would solve it all. Let me explain that a little bit more. So here's your equation, f prime equals f over 1 plus v source over v sound. So we said v source would be positive if it's moving away. Sure enough, that is our away equation on the top right. But if the source is moving toward the observer, use a negative velocity for the source. So v source would be negative, and it's going to restore the other equation. And this is what it would look like. You'd use a negative velocity, and then that bottom would become 1 minus v source over v sound, which is what we had to start with right here. In the next video, this talked about when the source of the sound was moving. And we've got a good equation for that now. In the next video, we're going to talk about what if the observer is moving.